Okay, so today's class will be a little bit different than what we've done the last few, in which it's mostly going to be you all going through the homework we did and kind of working through various problems. That will, I assume, take up most of the class, and so I don't anticipate we'll get into new content today. As a reminder, we have Alex coming to join us on Thursday. So if you have not gotten and downloaded and read the journal article that I posted to my website, please do that and come prepared with questions. They can obviously be on the physical side of like what's actually happening and what don't you understand, but also in terms of if there are questions about the mathematical ideas, like this is the time to do that, which is also often something you can't really ask. If you're at a conference and someone's paper has some mathematical concepts that you don't get, it's really hard to kind of be like, hey, I don't understand how you did this calculation. But that is the goal of something like this, or I hope you actually can kind of bring out where you were confused or not in terms of the way the math was performed or presented. And so please read that yeah, come prepared. How was the first homework assignment? Okay. Others? Let's look over there, but yeah.
It wasn't bad. I don't know.
Okay. That was Go ahead. Sorry.
I wanted to say I struggled with the third one a little bit. So that's
the bouncing ball one, right?
Yeah, like for choosing the parameters, like I think I was overthinking it, and I was just kind of picking the right parameters and stuff.
Yeah, that was, and so I leave that one to have kind of the most vague way of asking it, kind of on purpose, just because, as a researcher, you're kind of the spectrum of problems you see kind of range from like the well-defined to the, I wonder how I would even begin to think about this. Someone emailed me kind of asking like, okay, well, how do I know? How do I know what parameters are right or wrong? And so I'll repeat the answer I gave to that student here. And one thing I like to say is, you first want to make a decision and follow that decision through and come up with some sort of a model. And then test that model against your intuition. So for the ball bouncing one, you kind of know if I drop the ball, well, the height that it bounces back to has to be lower than the initial height. Okay, that's good. You also kind of know that it should be like not dramatically lower. It shouldn't be like if I drop it, it's going to come back to like 1% of the initial height. And you probably would guess that it probably is not going to come back to like 99.5% of the initial height. On top of that, I think once you have a model and it sort of matches your intuition, like, okay, hey, it bounces, it comes back not to the same height, but yeah, it's pretty good. I think it's kind of your job to switch gears and to become like a lawyer trying to break apart your case. And so it's almost like look at your model and just try to pick a hole in it anywhere you can. Like, what would be a counterexample that would break this model? And that mentality of kind of switching to like, okay, now I have a model. Now my goal is to break this model can really help. Because for one thing, you might not consciously realize this, but that's what your advisor is going to do when you bring him or her an equation. They're going to look to see, okay, I'm going to play devil's advocate here and break this thing apart. That's also what's likely to happen when you present it at a conference or when you submit it for peer review to a journal. They're going to be looking for like the simplest way that I could break this model. And so that doesn't mean that it's easy to do that, but it's kind of if you switch into that mentality of like, okay, I have a model, I'm going to assume it's correct, and I'm going to take on the role of trying to, how would I break this model? What would be an example of something that would not work? and would show that this is incorrect. And that's kind of the best you can do. And these problems are a little unfair in the sense that, you know, in reality, you wouldn't just be kind of mentally sparring with yourself to see if, like, if I have the right parameters or not. In reality, what you'd be doing is you'd have a model, you'd kind of mentally spar with yourself about whether or not it makes sense or not, and then you would go and collect data somehow, either experimentally or running a computer simulation to see how that compares. And so in your actual research career, you know, you're not going to be on an island as much where you have to just rely on ideas and then other ideas to refute or confirm your model. That's the way I would recommend approaching it. But know that, like, in the confines of this class, it's a little bit harder than it will be in the real world. Because in the real world, you'll be able to go and test some of these ideas out. Where in this class, you're kind of like, well, yeah, that sort of makes sense. This is the furthest that I can take this without going and doing a lot more work. So that problem was supposed to be hard because of it was vague. So I don't know if that makes you feel any better, but that's how I would recommend it. Yeah.
Another sort of general thing I ran into, a couple of the questions expected us to find some sort of a unknown function, similar to what we did in the lecture. So I went back and I looked at the brittle fracture problem we solved in lecture, where we found that unknown function alongside whatever our dimensionally reduced form was. And I realized that that step, at least in lecture, where you jumped from the dimensional analysis to a form with the unknown function, was a little opaque to me after looking at it the second time.
Yeah.
I was wondering if you could either touch base on that general idea there again, or.
Yeah, so let me repeat the question for those online. So if I understand what you're saying, it's kind of like you have a scaling in which it says, like, A scales as some parameters with dimensions times something dimensionless to an unknown exponent.
Yeah.
And then we go from there and we say, okay, well, in reality, it's not unknown dimensionless parameter to an exponent. In reality, it's mostly, we should think of it as A is equal to dimensional quantities times some unknown function of the dimensionless group. Is that at least part of what you're getting at?
Kind of, yeah.
Yeah, so, okay, so that's almost like you can kind of directly write that down, assuming that where it comes from is this fact that if you have let me write here to help. There we go. So if I'm understanding correctly, you're kind of saying, you know, we would often find something like, you know, capital A scales as, I'm going to write down some random variables. We'll say like X and Y times Z over B to the little a. And then we usually go from here to a, you know, really equals XY times some unknown function of Z over B. Is this step kind of the question you're asking about? Okay. So this step is mostly you should think of this as more of a rule than anything you need to do. And why? The reason why it's a rule is because we don't really know anything about this quantity or the unknown factor that's probably like some constant out here. I'll call that constant, I don't know, what should we call it? We'll call that constant alpha. So the things in red, because it's dimensionless, there's no reason why we can't simply say a different solution would be alpha 1, xy, z to the b to the a1 plus alpha 2 . Those are all equally valid because we don't have any reason to say that it's just one term. It could simply be two terms. And nothing has really changed because all we've done here is think about this dimensionally. And dimensionally, this top line is exactly the same dimensionally as this bottom line.
So to back up a second, our understanding or like a condition for applying this rule of just saying whatever is to the unknown exponent is part of some undefined function. In order to do that, we have to assume that what's inside that exponent term is dimensionless. So that in this case, z over b, or whatever form that might take, will always be dimensionless.
Yes, and that should be clear to you when you go through and it's the parameter inside the parentheses that's being raised to some power is always dimensionless. If it's not dimensionless, you did something wrong.
Okay.
So the terms outside of that where you kind of know the exponent, so I'm going to write, so like these terms here where I happen to have both of them to the 1, we know the exponent, the dimensions of the product x times y are going to be equal to the dimensions of A. And so if I were to then say, rewrite this, I could say that A over xy is equal to z over b to the A. Where the left-hand side now
Is
is dimensionless, and the
right
right-hand side is dimensionless. And this should always be the case. So if once you get to here, this is dimensional. These two things are the same dimensions as this, and then what's left as your unknown should be dimensionless. And because it's dimensionless, if this is a solution, this is a solution. And if this is a solution, it could also be alpha 3 times xy to the log of z over b, because that's also dimensionless.
Why is the sum solution?
Because
How are we making that jump, that first part? If that first part works, then
because all we can tell, so the question was, how do we make the leap from here to here? In which we were kind of saying, if this is a solution, this is also a solution. So the reason we can make that leap is not to say that this is a solution. It's saying from dimensional analysis alone, we can't rule out that this is a solution. Because all we know is that this is a dimensionally consistent equation. Units of this equal to units of that times a number. This is also a dimensionally consistent equation. The units of this are equal to the units of that. We can only add terms that have the same units. This one has the same units, so that's fine. And this is a number, and this is a number. And so we're not saying this is a solution. We're saying from dimensional analysis alone, we can't rule out that this is a solution. And so therefore, this is not really an appropriate form. This is an appropriate form where we're saying dimensional, these two items are dimensionally consistent, and then we have some unknown function of this number, z over b. That function might be additive, or it might be some complex log or exponential function or anything else that's going to take in a dimensionless quantity. Any of those we can't rule them out as possible solutions. So the best thing for us to do is to say, we have some unknown function that we would like to determine. And sometimes that function is trivial, like in the case of the Eddington work, it is a summation. Okay, that's a really trivial relationship there. We can't figure it out in dimensional analysis alone, but it's a solution. We can't rule it out as well. Yep.
I
Another
want to
question?
ask a similar question in the first class. I still have to understand why the XY part in this equation cannot be in a different form, keeping the dimension the same. Like exponent of XY, the dimension is the same.
Okay, so the question is, why do we know that this term here doesn't enter as some dimensionless quantity as well? Is that what you're
No, I'm
saying?
saying like if XY still has dimensions,
Yeah,
why
right.
can't you put it like to the B, for example? Because the dimensions. She's saying that the dimensions would then still be the same, but they're
Right.
not necessarily. Depending on.
Okay, so I think if I'm hearing the question correctly, it's, why can't we take these two things to a power to the B? Is that fair to say?
So I think, yeah, for example, why doesn't the A cannot be like exponent of XY and function of dimensionless number?
So why can't A be equal to the exponential of xy times the dimensionless number?
Yeah, right.
Okay,
Or the function of dimensionless number.
because you can't take the exponential of a dimensional quantity.
Oh.
And you
Why?
can't take the log of a dimensional quantity. You can take the log of a number or the exponential of a number. And so there's two parts to this answer. So one of the reasons is you can't you can't take exp of a dimensional quantity. It has to be dimensionless.
Oh.
The second part, which is probably a little bit more general, is to say that I need this, in order for this equation to be mathematically correct, the units of the left-hand side have to be equal to the units of the right-hand side.
Yeah.
And so that's, if I take, I guess maybe that's where the mix-up is. If I took the xy, exp to the xy, then it has to be dimensionless, and then therefore I have a dimensional mismatch.
Mm.
Does that answer your question?
Yeah, okay, so in general, we cannot take exponent, exp for dimensional number.
Exactly. You
Oh,
cannot take the
in general.
log or the exponent
Oh, I see.
of a dimensional quantity. It has to be a number. It can't
Oh,
be,
interesting.
yeah. And that's why you'll always see like, it's going to be like exp times a time divided by a characteristic time scale, or like or like a length divided by a characteristic length scale. You're gonna always see logs and exponents of numbers, dimensionless quantities. Other general questions?
I had a question related to this. So for like the second format, so the second line, how would you express that, but when you have two pi groups instead of one?
Sure. So let me first answer with the proper way to express it, and then I'll get to I think with what you're asking. So if you had two pi groups, then what you really would want to say is something like this. A is equal to xy times some function that takes two inputs, and that two inputs might be pi1 and pi2. So this is a function that's kind of asking for two inputs and is going to give you a number out. So this is the proper way to write that. So this is kind of like, you could think about this, maybe it's helpful to think about this way. This is really identical to saying, f of x and y. So I have some function that takes in two spatial coordinates and spits out a number. Maybe it's going to spit out the z component or something like that. So this is the proper way to write it, where you're saying, I have some quantity that depends on this quantity. These two things have the same dimensions. And then it also might depend on a couple of numbers that come from the parameters in the problem. This is a number and this is a number. And we don't know the function that takes those numbers. And that function can take as many arguments as it needs. So you could have as many arguments going in here as possible. Writing it out in this way is a bit more complex because in reality, what you would find is that it's going to look something like alpha 1, xy, I'll show this as pi 1 to the a1, pi 2 to the b1, plus alpha 2, xy, pi 1 to the a2, pi 2 to the b2. But I want to make it clear, this is the kind of correct representation of it, because we don't know what the function is. This is basically a possible solution, but the actual solution might not look like this at all. It might have only, it might have a difference between two quantities, and one of them might have an exponential, and then there might be some log term or something else that takes a dimensionless form of pi 1 or pi 2. So this is basically a reason why it's inadequate to write this. This is basically like a reason why we need to write it more generally as this, where I have velocity equals velocity times some function of numbers that takes, in this case, 2 arguments. And we don't know what that function is. That function could be as arbitrary as you could as imagined. Does that answer your question?
Yeah, that answers my question. Thank you.
Okay. Other questions? Anything in the chat? Let me just check. Nope. Cool. Does anyone want to get started and go through the first problem? If you're at home and you want to, either yell it out or mention it in the chat, and I'll make you a co-host, and you can kind of just go through your assignment. If you're not and you're here, you can just kind of come up and use my iPad if you're so comfortable. Just a heads up for those of you who might be kind of nervous about making a fool of yourself in front of your classmates. Every time I teach this class, I think for every single homework assignment, maybe not, someone has volunteered and presented a completely wrong answer. And so if that is you, you're not special. That is how it goes. These are hard problems. It's gotten to the point where I've had students volunteer saying, I didn't finish this one. I'm pretty sure I did it wrong, but I kind of want to show you all, so maybe you can help me figure it out. So that is more of the spirit that I'm hoping we take this in. This doesn't have to be perfection. It is more for us to kind of learn, both in terms of how we explain what we're doing, but then also in terms of kind of rethinking or at least questioning the assumptions we made in solving the problem. So if you're worried about coming up here and doing it incorrectly, that always happens. So don't worry about it. It's pretty typical.
Need a volunteer.
Oh, cool. Woohoo! All right, so I'll go in order. I can give it a try. All right, cool. So Jacob, I'm gonna see if I can share the screen with you. Okay, so we'll see how this goes, I think, and then.
Right. Can everybody hear me?
Yeah.
Yeah, I can hear you.
Okay. So you should be able to share your screen if that's helpful. Sweet. Awesome.
Yeah, so it should be a PDF. Can you guys see that?
Yes, and could you maybe I should pull up the homework so I can remind people what the question is, maybe. Let me do that really quickly. Let me just throw the question up there.
I don't think I'm able to share two windows at once.
No, that's okay. Let me see what I can figure out here.
It's weird because the different entry is exactly the same as me. Feels like
Okay, I'm gonna steal the screen from you for just a second, just to show everyone what we're doing, and then I'll give it back, and hopefully it still works. Okay, this is the problem on the luminosity of giant and supergiant stars. And the hypothesis was that the period depends on the star's average radius, its mass, and its gravitational constant g. So we start with Newton's law of gravity. And from this, I just wanted to make sure that you can determine the fundamental units or dimensions of g. Then use dimensional analysis to determine a dependence of p on the three parameters, mass, radius, and gravitational constant. And then, and this is, I think, one of the more important points, is comparing what you found to the actual problem that was solved analytically by Arthur Eddington. And so let me turn this back over to you. All right, I think you're still a co-host. Yep, okay, cool. Now you can take over.
All right, it looks like it's showing up there. So,
Perfect.
so yeah, I guess I'll just get into it. So P is some function of radius, mass, gravitational constant. So the first part gives us some other relation. You know, F is equal to the gravitational constant times m1, m2 over d squared. So there's one term on each side, so we can equate the dimensions on each side to figure out the dimensions for g. We get that the dimensions for g equal the dimensions of f times d squared over m1, m2. So if we write all those out and simplify that, we get that the dimensions for g are L cubed over mt squared. So that's the first part.
This is a very common unit of measure, or I guess or constant. So how did you know you were right? Did you check it?
Yeah, I looked it up on Google. So
cool.
Yeah.
So just confirm, and that's fine. Like, please don't, feel free to do that. Awesome. Questions on this first part? I assume this part was pretty straightforward and pretty easy. Okay, cool.
So the second part wants us to find the dependence of the period on radius, mass, and the gravitational constant. So this is just like what we did in class. The dimensions of period are equal to the dimensions of radius to the A, mass to the B, gravitational constant to the C. So then we write out the dimensions. So time equals length to the A, mass to the B, length cubed over mt squared to the C. And then we consolidate the exponents for each dimension. So we've got on the left side time to the 1, then on the right side we have length to the a plus 3c, mass to the b minus c, and time to the negative 2c. So then we can make a system of equations. So 3 equations, 3 variables. We get the straightforward answer. We can plug that in to our original equation, and we get that the period scales with r cubed over gm to the 1/2.
Hold on one second, we have a question.
Why isn't doesn't the problem definition say that P is the luminosity of a star?
it's the period.
P should be the period of the question was
Oh, sorry.
what is P? Is it luminosity? And I think the question has P as the period, which depends on R, M, and G. where's the luminosity comes in.
It says the luminosity of a certain giant and supergiant stars varies in a period. Oh, so when you're looking at a periodic variation, do you assume that whatever other unit is there sort of normalizes out and you're just left with the time?
Yeah, so the question for those at home is kind of trying to reconcile the connection between luminosity and period. And think about this from the problem of an astronomer. They're looking at the sky and seeing these giant stars, and they're seeing that the brightness of the stars increases and decreases periodically. So you're seeing something that gets brighter, gets dimmer, gets brighter, gets dimmer in some sort of cyclical manner. And so the question is, how does the period that you're observing depend on the properties of the star? And so it's not the actual, you're not going to learn anything about the measure of the luminosity. It's mostly the way that the period of that quantity is changing. And that's why the units of luminosity don't enter. What we're looking for is to see how does the period of this thing that's happening depend on the size of the star.
So just to clarify, in this problem, we're looking at the period and its dependence on these three parameters. And then out of the scope of the problem, we're just told that the luminosity depends on the period, right?
Yeah, I should say it a different way. The luminosity varies periodically. And so I think you can think of this as like, you're looking up at the night sky and there are three different giant stars and they are becoming brighter and dimmer at different frequencies or with different periods. And you know that one star is bigger than the other star or made of different materials than the other star. And so your question is, okay, I'm looking at this, the periodic dimming and brightening and trying to question, how does that depend on the size of the star? How does the period of that kind of oscillation depend on the period of the star? And so we're not actually concerned with the luminosity itself. We're concerned with the variation in the luminosity or the period, the way that it's changing. So you were correct to do it based on a period, which is why it worked out with the units the way it did. And then to be clear, not considering the luminosity or not considering like the kind of the thermal aspect of this is why we are unable to get the exact analytical answer. And that's what Arthur Eddington is doing. He's saying, okay, well, let's pretend this is a heat engine in which the cycle of this heat engine is going to vary in a certain way. Then we can arrive at a period for that brightening as such. So I hope that clarifies some confusion there. Okay, so yeah, go ahead with parts. Just to be clear too, if we didn't know anything, if I didn't tell you anything about the analytical solution, you kind of just have to either hope or test your hypothetical model based on data. Here we have something to compare it to so we can actually see how does our model that we arrive at just from dimensional analysis compare to what you would do with a more sophisticated calculation. All right, part C.
All right. So yeah, the third part says that this guy, Arthur Eddington, came up with this equation for the period. So I called it P subscript AE for Arthur Eddington. And it's the square root of 3 pi over 2 gamma G rho. And we know that rho is average density. So, and since it's a sphere, we can write it as mass over 4/3 pi r cubed. So then I plugged that into his equation and simplified it, and we get this equation where the period equals the square root of 2 pi squared over gamma times r cubed over gm. And we can simplify that further to say that Arthur Eddington's period equation is equal to our equation alpha times r cubed over gm to the 1/2, where alpha in his equation is this 2 pi squared over gamma to the 1/2.
Excellent. Really good. Hopefully this, I think that was a nice clear explanation. Hopefully that makes sense. Just to for the sake of being doubly clear here, gamma is a ratio, so it's a number. So everything in alpha is a number. Now the number for gamma might depend on the particular star, but at the end it's still just a number. And so everything in alpha 2 pi squared over gamma is some number that we are unable to say anything about using dimensional analysis. It's just an unknown dimensionless quantity. And so we did pretty well. By just the back of the envelope calculation, did pretty well for calculating the period of these giant stars. If this problem is at all interesting to you and you don't have any idea who Arthur Eddington is, there's a cool movie on HBO called Einstein and Eddington. Eddington's the one who did the experiments to confirm Einstein's theory of general relativity, which was a really big deal and annoyed a lot of people because everyone in England was super protective of Newton, let's say. And so to have someone come in and say Newton was wrong was quite a controversy. The movie is actually pretty well done and kind of goes through like the political drama and all the science as well that kind of went into this big experimental measure that Eddington did. So cool, thank you.
Yep.
I will not assume that the person who volunteered, Alita, I will not assume that you also volunteered to do number 2, but if you do want to do number 2, you're welcome to.
I can do number 2.
Okay, cool. So let me make you co-host. All right. And just while you're setting up, let me just share my screen really quickly to remind everybody what number 2 is, because you're just looking at your solutions. So number 2 is a problem of droplets. You drop a droplet of some fluid, and what happens, and you've probably seen cool videos of this, of a splash forming with like a ring of spikes, something that looks like a crown. And if you do these experiments, you can basically use your iPhone or smartphone as a high-speed camera and do this with like a droplet of milk or something at home. And you'll see that in slow motion, this thing will form these beautiful crowns with a certain number of tips, I guess, to the crown. And that depends on the fluid, and it also depends on how fast the fluid's hitting the surface. Droplet splashing is a supremely complicated research question. I remember when I started my postdoc, there was, well, there's been interest in this topic for decades, but I remember someone giving me the advice of like, stay far away from this. Like you can never have a fast enough camera. You can never measure everything you want to. It's really, really hard. So that's not to dissuade anyone interested in it. It's just to say this is a hard problem. This particular part of it, of like how many parts of the crown do you see during the droplet formation, is less complicated. But a lot of the other aspects of droplet formation is a really rich and complicated problem in fluid mechanics. So I will stop sharing and let you walk us through the solution.
Okay, let me share my screen. Okay, so I'm just gonna work through it for everybody here. So as the problem said, we have the number of points in the crown, which is dependent on U, so the speed, R, the radius, the density, and the surface tension. And just for everybody's reference, speed is in units of meters per second, radius in meters, density in kilograms per meter cubed, and surface tension in newtons per meter. And they wanted us to eventually express this in terms of this constant, which is density u squared r over the surface tension. So I went ahead and just solved for this relationship. So we have n equals UA RB rho C, and surface tension to D. And as you can see, we have 4 different variables, and we're only going to have M, L, and T be in there. So that means we're eventually going to end up with our function in terms of one of these exponents, A, B, C, or D. And I'm going to end up choosing D, but you don't have to do that. You can choose whichever one you want. So then if we go ahead and actually write this out, we get L over T to the A, and I'm referencing all these units over here. LB, M, L cubed, C, M, T squared, D. So what I end up getting is for your L equation, you get A plus B minus 3C equals 0, which I'm going to actually keep going instead. For your T equation, you're going to have negative A minus 2D A equals 0. And then for your M equation, you're going to get C plus D is equal to 0. So if you solve the system equations, you get C equals negative D. Again, I'm solving in terms of D, but you don't have to do that. A is negative 2D, and B equals negative D. So and this means that N is going to be proportional to U minus 2D, R minus D, rho minus D, and then your surface tension to the D. So we can properly write this as, and it's proportional to this, which is also N equals alpha 1 over, I'm rewriting it in terms of this, which they asked us to D, or it can also be expressed as N is equal to F function of that. So that's for part A, or for the first part.
I'm just gonna, that's great. Any questions on this? Yeah.
Technically, is the second expression technically correct?
Negative A minus 2D equals 0?
The
No.
the second part of the second expression of M, N. So
This one?
Yeah, right. Because you actually don't know if it's an exponential or some more complicated function. You cannot actually use equal to that second expression. It might be.
Yeah, so the question is it fair to write it with an equal sign, having it written as 1 over the Weber number to the D? And this kind of gets back to the point we were making at the beginning of the class. Yeah, like to be kind of technically correct, you'd want to write that it's N is equal to some unknown function of the Weber number. Or in this case, you could write it as some unknown function of 1 over the Weber number. So that would be the kind of more accurate way to use the equality symbol. I think if you want to keep it in this form, I would probably kind of leave the scale symbol or leave the some approximate symbol there. And oftentimes you might do that as like a first guess, like, oh, maybe we're going to be lucky and it's just going to be proportional to the Weber number, which in this case it is. But yeah, so to be kind of more mathematically sound, we would want to say that the number N is equal to some unknown function of the Weber number, or 1 over the Weber number. So yeah, that gets back to what we were doing before, and that's correct. But everything else here is really good and correct. So I will just
Okay.
say
Oh, go ahead.
in fluid dynamics, for those of you who study fluids, you will know that there are just dozens of numbers named after famous people. This is one of them, but they usually represent a balance, a dimensionless balance of two important quantities. And so the Reynolds number is, you're balancing viscous and inertial terms and saying what matters, is viscous dominating or is inertia and turbulence effects dominating. In the case of this problem here, it's framed in terms of the Weber number because it's asking, what matters more. This is the Weber number is a balance between surface tension and inertial terms. And so you're kind of saying for a large Weber number, inertia will matter more than surface tension, and for a small Weber number, surface tension will matter more. And just to be clear, we have 1 over the Weber number here, which is why it looks opposite to what I just said. But the Weber number is kind of inertia over surface tension. And so it gives you a way of looking at what are the dominant effects in your problem, which can help take the Navier-Stokes equations and reduce them significantly if you know what you can neglect or not. And so that's why I asked you to put it in terms of the Weber number, because in this problem, it's really this competition between inertia and surface tension that's going to dictate the phenomenon we see. But that's just an aside. So thank you. You can carry on.
Okay. So for part B, I ask you to express U in terms of H, and then rewrite your answer for part 1 in terms of H. So I just went back to your basic kinematic equations. And if you remember, there's one that expresses velocities in terms of just acceleration and the distance traveled, which is that one. You can also derive that from the rest of kinematic equations if you want to. So this ends up giving you, if we just put it in our terms, it gives you U squared equals 2GH, which we can then simplify to be U equals square root of 2EH. So that is just rewriting U in terms of H. And then if we plug this into our equation from part A, we get N equals a function of surface tension 2GHR, and then your density right here. And then I'm just gonna move on. So for part C, it tells you basically that they find that it's a linear relationship with a slope of 1/4. So it means that a linear relationship N equals H plus B, where your slope is equal to 1/4 right here. So you know that it might look something like this from the information they're giving you. So if we go back just to our equation, we had N equals function of this, and we know it's linear with a certain slope. So we know it's gonna actually look something like this. Where it's actually gonna be a power function, and that's just gonna be 1 right here because it's linear. So I'm just gonna get rid of it. So then if we just rearrange this to kind of write it as a direct linear relationship to H, so it looks more like the information they gave us, we get alpha 2GRB, or surface tension, times H. So we have like this whole thing at the front, right? And this is an unknown. So we know actually that since the slope is about 1/4, this means that this whole thing right here has to equal 1/4. And they gave us the information that the radius is 3.6 millimeters. Density is 1.1014 grams per centimeters cubed. Surface tension is 50.5. And what I did is just to make my life easier, I just converted all these into the same units. So it says 0036 meters, 1101.4 kilograms per meters cubed, and 0.0505 newtons per meter. I might have done some math wrong here at some point, just as an FYI. But this is what I got for my conversions. So you go ahead and just plug this back into basically this equation here, so you can solve for alpha, which is what they're asking you. So you get alpha is equal to 1/4 2GR this, which is 1/4 0.0505 over 2. I approximated gravity as 9.81 to 61101.4. So you end up getting alpha is equal to 1.62 times 10 to negative 4th. And again, I might have gotten my math wrong. I didn't actually double check these conversions in math, but that's what I got. And then at the end, it's telling you, okay, if you have 80 spikes, so n equals 80, what height do you have to have? And we already know that our relationship that is given to us by them is n equals 1/4 h. So it's actually just going to be as easy as doing, so if we rewrite this as h equals 4n, so then it's just going to be h is equal to 480, which is equal to 320 centimeters. Right here.
Excellent. I got 320 as well. Are there questions on what we did here? Thanks for walking through it. That was helpful.
No problem.
Yeah, what's up?
Where did you find the unit of H?
So the question was, where did you find the unit of H? And I think it just says drop it from a height.
Yeah, I mean, so they gave us the information like the relationship between N and H is like slope of 1/4. But I think you need a unit to say 1/4 or 100 over 4. So I look at the textbook actually, and the graph says it's like centimeter.
I thought the problem, I don't remember what it said. I thought it said if you drop from a initial height h. So you could do h in what, in part 2 of it, the bullet point part 2 says the value n has been measured as a function of the initial height. So I just assumed that you would take height as a length.
Oh, so what I mean is, so if you don't know which unit you use for calculating the slope of about 1/4, you cannot actually get the unit of the last question. So we know that because the slope is 1/4, so we know the number should be 320, but we don't know if it is millimeter, centimeter, or meter.
I don't think so. Well, I think you're told that it's, well, you're saying you don't know if it's millimeter, centimeter, or meter. Oh, so I mean, no, I think but based on the unit conversion that was just walked through, I think you would get, a unit would drop out. And I think you would get either in terms of meters, and then it would be like 0.32 meters or something. I think you would, following the unit conversion up here, I think you would, from the kind of unknown constants here, be left with a unit. So this quantity here should give you a unit of 1 over length that would cancel out with this length.
Oh, but for the really very last question, to get the points of 80 points for the crown, how high?
I think you would be left with when you're doing this,
Yes.
the combination of these things should leave you with a length unit. Like and it wouldn't just be arbitrary L, it would be like millimeters or centimeters, depending on what you, I think she kept it in meters, so it would be probably meters, and I think just convert it to centimeters. I think that this quantity here should give you should be left with something times 1/meters.
I sort of see what she's saying. If you do the math for like the blue part of the circle in blue, you would get, let's say, one with some length, which is what you were saying. But how do you know if that's meters, centimeters? Because the unit, let's say the parameters you provided, you're scaling them to be all in meters. But how do you know that that's equal to 1/4? Because you're getting like one point for every, let's say, 4 meters or 4 millimeters.
So let's forget about the other things. So let's just talk about the last question. So everything we've done here is just multiplying 80 with 4. So we get 380. Right, but how do we know what kind of unit we need to use?
It doesn't matter, right? I see what you're saying, but if you have, say by your logic, there was, say by your logic, you're using centimeters and you're scaling at centimeters, convert that to meters. What happens? You're still, even if you're just going from 0.01 meter to 0.04 meters, that's still the equivalent of linear scaling in that metric sense. So what it depends on isn't necessarily the absolute units of the slope as it's defined, but the relative definition of the units that were given in the problem. I can visualize this a lot better than I can.
So I think it's a good question. I'm not sure if maybe I worded it confusingly, but I thought my understanding would be is if you followed through the unit calculation there, you should have some 1/length left over. And it should be, because everything was converted to meters, it should be 1/meters. And so I think if you do this part,
What happens if you convert everything to 1/millimeters?
A linear scaling is still a linear scaling.
yeah, that would be fine. You would just get a larger number here. Yeah.
So, I'm sorry, I think I still don't understand. So forget about the alpha. For the last question, I think I'm just repeating. We just multiply 4 with 80.
I think the goal would be to say,
We didn't put it back to the original equation. We just multiplied 4 with 80 and got 380.
Well, she had already kind of accounted for that in the way she solved it out. So when she solved it out and came to her answers for alpha and everything, there's an intuitive conversion to centimeters that she hasn't written out explicitly.
Where
It's
where
okay,
we
I'm
converted from meter to centimeter.
I'm making a jump in my head there, but that's done. But I'm sure if you just plug the numbers in, you'd find that basically.
I'll try to, I don't have I think I'm a little confused, and I will.
Yeah, maybe I can ask question after.
Yeah, I'll try to go through this again to see if I can understand where you're getting at. But I think the idea is correct as presented, which is you have these dimensional quantities that are given for R, rho, sigma. That should give you a quantity that's like n equals alpha times 1/length, which is a number, times h. I think it would make, I guess the question is more so of, I think maybe the question maybe you're asking is alpha 1/4 or is alpha times that dimensional
No,
quantity
I
1/4?
I got the other part on the top. But
Okay.
I just don't understand the purpose of the last question. Because besides all the dimension analysis and alphas and getting the parameters and prefactors, we can just solve it without any information.
Yeah, that's fair. So I get what you're saying. So why do we not need to use the alpha?
Yeah, because if you know
Yeah.
the slope is 1/4, why do we need to use the dimensional analysis? Because we can just
Yeah,
multiply it.
fair. That's a fair question, and I don't have a good. I'll come back to it. So I guess the ultimate question is do you need to do any of the work above this line? Because you really just multiplied 4 times 80 to get 320. So I will double check that. And maybe I worded the question in a confusing way, but I'll double check that. Yeah, but I think that's a fair point. Okay, cool. Well,
So
yeah.
can you guys hear me? So what if the 124 is not the whole thing, it's just the alpha?
Yeah.
So the 2g times the r and the rho to the surface tension is another dimensionless group, right? So because we have 3 known factors, the r is 3.6 and the rho and the, so if you only use the 80 to time 4, then the next question is, I don't think the question is designed to plug this, right?
Yeah, that's kind of, I think that's what I was getting at too. I think maybe what's actually is taking alpha to the 1/4 times this quantity, whatever this thing works out to be when you put all the numbers in. 1/4 times that equals times h would equal n, and that might resolve this question because
because I calculate it that way. So the h should be like 4 meters. So because I don't just calculate like 80 to time 4 to be 320.
Yeah, I think that makes sense. I think that's what I think I should have been more clear in writing it to say that the alpha is kind of 1/4, and then you're going to have to multiply that by this dimensional quantity, which is going to be a 1 over length, and then multiply that by h, which is a length, to give you the dimensionless number, and you're basically, from the combination of that, getting the number on the crown, setting it equal to 80. And so maybe,
But would that still give you a direct linear relationship with a slope of 1/4 though? Like if you did that?
Yeah, my point is here. So if you think of the n is not singly dependent on h, it's also dependent on another dimensional, like r times rho to the surface tension.
Yeah, like it is, but like in the problem, it's stating that like, okay, we know through like experimental data that the relationship we found is a linear relationship with the slope of 1/4. So
Right, because in
think
this,
this is a wording issue. I don't think there's any way to from the way I worded the question to know which one is right. I think both of them you could arrive at based on the way I worded the question. It's completely reasonable to say, oh, this means alpha times that quantity is 1/4, or it means alpha is 1/4. There's a quantity. I think the question is vague in that way, and so I don't think it's. I don't think doing it this way is like necessarily wrong by the way that I framed the problem, because you could interpret it one way or the other. But I think, and I'll double check this, I think what I was trying to say was take alpha as 1/4. This quantity is going to be something, and then if you combining all those, what would the height be? I'll double check that to make sure, but I think both of those approaches, based on how I worded it, are reasonable. So this might just been my problem.
Actually, no, I think the wording is consistent because it's saying it's proportional to the height, but all of those parameters, G, R, rho, sigma, are physical properties of water. So if you found that it's proportional to height, it's not that those physical properties of waters in the experiment are going away. It's just, I guess you should have said proportional to height when experimenting with water droplets.
Yeah, with a fixed, with some like
With a fixed material.
fixed material property. Yeah, so it's. I think it's my wording it confusingly that caused this challenge. So, so apologies there. I'll try to reframe this question. But thank you actually everybody for jumping in and helping clear this up. All right, cool. So the first two are pretty straightforward, I think, if you take away my kind of confusing wording of the question. And the third one is probably more similar to something you would find in an actual research problem in lab where you are curious about something, you don't really know what matters, you could probably guess some things matter, but it's not really that obvious what you can exclude or include. This type of thing is more common, the type of thing that I would sit down with while working on a problem, which is, what do I think matters? And I would end up developing 10 different scaling laws, depending on me assuming this matters or this doesn't. So this one's hard because it's vague, but it's vague because a lot of the problems you'll encounter in your research are vague at first when you first start thinking about them. Does anyone want to take a go at number 3?
I can do 3.
Okay, excellent. I'm just going to quickly show it and then I'll hand off the screen. So number 3 is a ball is dropped from a height of h naught. It rebounds to a height of h. What do you think matters? And assuming some functional dependence of h on h naught, how does this reduce your formula for the rebound height? So let me go back to sorry, actually, who said that?
It was me, Leah.
Okay, awesome, thank you.
All right.
Now be co-host.
Can everybody see? I think you can. Okay. I'm not super confident in my answer, but Sonny could pump me up to volunteer. So I'll give her credit. Okay, so we know ball dropped from a height h naught, rebounds to a height h. So instead of A and B, I did 3.1, 3.2, whatever. But so 3.1, identify the parameters. Yeah, so I wasn't really sure. Kind of what was mentioned, it's vague on purpose. So I sort of took a guess. I said that the height, I hope you can see my cursor. I said that the height was dependent on the density of the ball, the radius of the ball, and then the gravitational constant, in addition to the rebound height. Or sorry, excuse me. So I took this form of the equation here. And then I saw that we didn't have equal dimensions on both sides. So I figured there was some other parameter I was missing. Did a little Googling and I saw that the elastic modulus was the inverse of that parameter. So then if I put that in, then I got L for the length on both sides. So then I added that parameter in here. I don't know if there was a more technical way to do it, but that was just how I approached it. So then I did what we did before, A, B, C, D, E for the exponents. And then I got these pi groups. Again, I was putting alpha here, and now I'm learning that that's not mathematically sound, so we can ignore that. But I got, you know, for my first pi group, I got H naught over R. My second pi group, I got the density times R times G over the elastic modulus, E. And so again, like you can ignore that alpha, I guess. And so then I got R as a function of pi1 and pi2. And so then in 3.2, watch your eyes, I'll scroll up again. We assume that H depends linearly on H naught. So then if H naught is 0, H is 0. How does this reduce the formula? I'm definitely not sure about this part. But I assume, I guess because it's linear, I go back to my coefficients up here in 3.1. If it's linear, then I said that A exponent had to be 1. And so then if that's 1, then we get like R to the -1, which would cancel with this R here. So then I said H was a function of H naught, or sorry, H is equal to H naught and as a function of pi2.
Excellent. Questions? How do other people approach this problem? So I first want to point out that I love the way you started it with kind of like, let's assume as little things as possible. And then oftentimes what happens is you end up with what you found, which is like, oh, if I assume only these parameters, I don't have the right dimensions, so I can't go any further. And then you start adding in more stuff. And so I think Googling and figuring out like what could be this other thing, I think that's completely reasonable. That's what I would do. So I love that approach because that's fairly common, I think. So you just kind of, this is what I think is going to matter. Oh, look, it doesn't get me there. What am I missing? Go back, see what you're missing, and kind of add that back in. So I really like that part of it. And I think showing that is really helpful too. Did other people get something similar?
Yeah, I got the same thing as her.
Excellent. Anyone else? No?
I didn't incorporate density and volume,
Okay.
and instead I used compressibility or the bulk modulus.
Okay.
Now that I'm kind of looking at it, perhaps what might be, better to use if I use my approach was to do the ratio of the bulk modulus of the ball to whatever surface it's hitting, because that would kind of sort of mirror the whole theory of elastic collisions from how many other years ago.
So this is a good point that I'm glad got brought up, which is, it's one of the assumptions that's baked into what you're presenting here, Leah, is that, and you may or may not know this, and so but is that the ground that it's hitting is effectively infinitely rigid. And that's a very reasonable assumption. You're dropping a bouncy ball on the ground, and the bouncy ball is significantly softer than the steel subsurface or something. But it's kind of important to know that that assumption is baked in here. Now, if you decided to add that that modulus into the problem, what you would likely find is a third dimensionless pi group, which is a ratio of the modulus of the ball to the modulus of the ground that it's hitting. And then you would have to go through kind of the Buckingham pi approach and say, do I think this ratio is really large or really small? And then you would say, well, okay, I'm dropping a ball. Its modulus is probably on the order of megapascals, and it's hitting a surface that's probably on the order of tens to hundreds of gigapascals. So that ratio is very likely to be large or small. Perhaps I can throw that out. And so that's kind of hidden in here, which is totally fine. And I think you don't necessarily need to address that, but this is one of those things that once you got here and you tested it and it seems like it works, if you're going to go and write the paper on this, you kind of want to think like, okay, what did I leave out? Again, playing the lawyer, how could I break this? Well, I could break this by saying, well, what if I'm dropping my bouncy ball onto a surface of a huge bath of Jello? Well, like, I don't really expect it to bounce back as high. Why not? Well, now in that case, the modulus of the surface that it's bouncing on is significantly softer, or maybe even comparable to the modulus of the object that's falling. And so that's part of the assumptions that you would probably address in kind of writing, if that makes more sense.
Could you also justify ignoring density and volume based on the assumption that I feel like density and volume might factor in if you were looking at air resistance, But if it wasn't, then it's really just about, you know, the mass and you know, the velocity and the elastic modulus, which are bouncing together or whatever.
Yeah, certainly. So there's other things. I guess the question is kind of like what else might we be neglecting? And certainly, kind of the friction of the medium is being neglected here. And so whether that friction is air resistance or whether that friction is simply viscosity. So if I was dropping this into a pool, or I'm dropping this within a fluid bath of some sort, I wouldn't expect this rebound height to be the same, because now I'm going to have to compare the density of this object relative to and other parameters relative to the friction exerted by the medium that we're dropping within. So, and I didn't expect anyone to kind of incorporate all those things in there. I think the more common thing you would do is get here, test it with your experiments, and then go back and say, okay, well, what could I be missing? And that's kind of that point where I mentioned thinking like a lawyer, if you will. Like, how would I break this? Well, it's clearly not going to bounce as high if I'm doing this underwater. It's clearly not going to bounce as high if I'm dropping this on a really soft surface. And those are some of the assumptions that you may or may not have realized you baked into your model, but you can find them out when you try to break your model. Does that make sense?
Do we list assumptions on our problem set then?
What's that?
Do we list our assumptions on the problem set? Because as you said, like I did assume that it was like I'm bouncing a basketball on the ground.
Absolutely. Yeah, you can certainly list them if you want. And then that can be a way for me to kind of know, like, okay, this is, I don't want to say wrong, but correct in this regime, but unable to model the behavior in this other regime. And so I think in terms of, for the class, listing the assumptions is a nice exercise, but in terms of like you as a kind of growing scientist, I think that exercise of kind of questioning your models and questioning what assumptions might be there, whether or not you made them a priori or kind of you realize you made them based on kind of when you start to break down what you did, I think can be a really healthy thing, because it helps you discuss your model, when you're writing up your paper or your thesis in a way that is honest, I guess, and kind of self-aware, if you will, and recognizing the limits of the bounds of which you think is to be valid. So yeah, you can certainly write them on assignments going forward, but also just think kind of more holistically thinking about that as part of the process for your research will kind of pay off in the long run.
So I have a quick question on just like formatting and what it means. So like in this answer, the chess there is like h equals alpha h naught function of pi 2 with the second pi group. Does this mean that's always going to be like, we can always expect it to be like a constant times h naught times a form of pi 2? So it could be like log of whatever's in pi 2, exponent pi 2, whatever. Or could it also be like a constant h naught plus a form of pi 2? Like, does this like format like automatically mean it's like you're going to be you end up multiplying both of these things together?
So that's a good question, and that's something that'll probably, maybe not explicitly, but possibly be more clear as we progress further in the course. So I think Leah pointed this out, which is that when you write it as it's boxed off here in the bottom, you don't really need the alpha, because the alpha is essentially baked into the function. So it's not actually wrong to write it this way, because you could just pull the alpha out of the function if you want. But a simpler way to write it would be that h is equal to h naught times some f of pi 2. To get to the second part of your question, which is like, does it have to be multiplied by a function of pi 2, or why couldn't it just be h is equal to h naught plus h naught times pi 2? That actually is part of the function of pi 2. So for instance, if I said f of pi 2 was 1 plus 1 over pi 2, then my solution would be h is equal to h naught plus h naught over pi 2. Does that make sense? So like, the actual solution certainly could be to leading order h is equal to h naught plus some kind of small prefactor. So your function of pi 2 could be 1 plus log of pi 2 plus 1 over pi 2. And then when you multiply that by h naught, you see that at leading order, it's just h naught, and then you have these other terms coming in that follow. Does that answer your question?
Partially, but like, does this mean that like you're always going to be multiplying whatever f of pi 2 is times h naught?
Yes.
Okay. Okay, yeah, that answers my question. Thank you.
Mm-hmm. All right, that was good. All right, let me load up question 4. Okay, deep ocean waves. You can see my screen. The frequency of deep ocean waves, omega, is found to depend on the wavelength of the wave, the surface tension, and the density of the water, and gravity. So we use dimensional analysis to determine the functional dependence, and then compare this with the known solution. This one is sort of similar to number 1, in which we're comparing to a known solution, although number 1 I think has a very straightforward comparison. And this one you have to kind of do a little algebra and thinking to see how they compare. Is anyone interested in going through this one?
I'll try if everyone promises not to laugh.
There will be no laughing. No laughing. All right, stop. Was that Meredith?
Yeah, that was me. Sorry. Yeah.
Too many screens for me to monitor. Okay, you should now be co-host, and so therefore you should be able to share your screen.
Okay, let me just. Here, can everyone see it?
Yeah.
Okay. So for number 4, yeah, I did, mine's a little more bare bones than a lot of people. So the frequency is a function of these, it's the wavelength, surface tension, density, and gravity, right? Sorry. So yeah, just set it up. Wavelength, oh shoot, this was frequency, right?
Mm-hmm.
Okay, sorry, I think this is just a typo. I don't think it's, yeah, it's not repeated down there. This is supposed to be 1 divided by t. Sorry about that. Yeah, so then this is a length. This is a mass over second squared, kg per second squared. And then this is an acceleration. And so yeah, set it up like this and find the algebraic forms and then just solve it out. It's pretty straightforward. So yeah, I found everything in terms of C, and then got this at the end. Then you sort of clean this up a little bit, and you get G over the wavelength, the square root, and the wavelength squared times the density times gravity over the surface tension to the power of C, and that's proportional to this frequency. And so, yeah, I found that, and I think my reasoning is sound, but it's not super similar to the final, the actual response. Like there are some similarities, like this wavelength to -1/2, and then this is like, you know, but like, yeah, similar in our general form, but a lot of things are flipped. Like this row is to the negative instead of to the positive.
Let me jump in real quick. So is G over lambda to the 1/2 a unit of 1 over time? Because I feel like it's time.
Is.
So G is 1 over time squared.
Or did I?
No, maybe I'm just being slow. No, I think that's fine. Okay. Yeah, okay. So the question you raised about where rho appears in your equation versus theirs, remember that the dimensionless quantity in our unknown function, kind of like f of lambda squared rho g over surface tension, we don't know. It could be, obviously, it could be 1 over that quantity. So appearing in the denominator or numerator is fine. You can't actually tell anything about that dimensionally.
Right, sorry.
Did people get a similar answer or something different, or you got the same thing? What, you? Okay.
Sorry, I didn't catch that. What did he say?
He said I did it completely wrong.
Or I did it completely wrong.
No, I think I'm trying to remember off the top of my head. So you got the same answer? Yeah. I think there are kind of. I guess I'd like to see if anyone. So I think everything you've done up to omega is correct. I think the part that we could probably take some time talking about is, what is the functional dependence of that dimensionless parameter as it relates to the kind of given solution? Did anyone look into that a bit more? Because I think what you have for omega is right. That's what I have as well. Let's talk a little bit about comparing it to the solution, because the functional dependence in this case on your, if I can call it your pi 1, is a little less trivial than the case of the Arthur Eddington problem, in which it just was pretty clearly there. Does anyone have any thoughts on comparing the two solutions?
My answer, if you substitute the k into the given function, the next problem, you can take out the root of 2 pi and root of 2 over lambda. And then you got some function left, which is like root of 1 plus 4 pi squared times the dimensionless root.
Yeah, so I think what was said in class here, for those who can't hear it, is substituting k for lambda allows you to pull out like a g over lambda to the 1/2, and then you end up with a form that is a little bit more similar to the solution than I think is written here. So I don't think you did anything wrong. I think that you can kind of do some algebra a little bit differently to more directly compare the solutions. If you don't want to do that, this is an opportunity where, or for instance, like say it's not clear to you how to rearrange the equation, or like kind of what ways to manipulate the equation. Something that I do all the time is I will just kind of pull this into Mathematica and just start throwing numbers in and trying to see, okay, am I getting something that is similar, or like plotting it and seeing if I plot this as a function of, I know G, I'm going to pick a lambda, maybe I'll vary density. How does my solution compare to that solution? So that's like my kind of very lazy way of comparing. When I derive something that is like, should be similar to a known solution, but it doesn't look similar, I will turn to either graphical methods where I just start plotting my solution and their solution and say, oh yeah, they are the same trend. Theirs are just shifted up or down by 2 pi and mine's not. Because that process of kind of like manipulating or just looking for some kind of similarities and doing some algebra can be, I don't know, can be tedious. And so that's how I handle it. But I think everything here is presented right. I think you could probably compare the two forms in a different way. But I think that your prediction for the period, or forget whatever a frequency, I guess, is spot on.
Thank you.
There's one more question here, so hold on 1 second. Yep.
So the first term for the we cleared it up. Like, so 2 pi over lambda to the 1/2 times lambda over negative 1/2. Right.
I'm looking at this one.
Yeah, right. So the first term,
Yep.
you multiply and G and remnant, right?
Uh-huh.
But in the original equation, given the question, I think you don't get remnant. So that's what he drives.
Oh, okay. You're saying the term that's given.
Yeah, right.
Yeah, but the term is given in terms of K, right?
Right.
So GK is like G over lambda.
So you don't have to round that in the first term?
Well, but you do, right? Because isn't the first term GK?
Really?
Yeah.
The first term, I think.
Oh, I mean, you don't have rho.
No, you don't have rho in the first term, right? Yeah. So you mean pulling this term out here?
Yeah, right.
Yeah, this term should really just be into the second term.
Oh, I'm sorry. I think I misunderstood. So the equation you have on the 4B is you rewrote your equation, right?
Exactly. I think Meredith rewrote her equation in this form and was trying to make a comparison between the two. Yeah, exactly.
Yeah, sorry, that wasn't clear. Yeah, this is expanded a little bit to make it clear.
All right.
Should I stop scaring?
Yeah, that's perfect. Thank you very much for doing that. Let's see.
I have a quick
Yeah.
solution to find. So
Okay, excellent. So do you want to share, would it be easier for you to share your screen and go from there, or do you want to come up here?
I can just copy it onto your.
Okay, cool. Let me
I haven't logged into the Zoom yet.
no problem. I'm sharing my screen. All right, so you can come on up here and right here, and if you just, the microphone's over here, so if you're talking loudly, it should be okay.
So, let's see, right on here and then right.
If you write down here, it's easier to write, and then it'll show up there.
So, number 5, the problem was, I'll just reread it. A ball, when released underwater, will rise towards the surface with a velocity of v, dependent on a couple of parameters. So you can write those out as, so v is dependent on L T inverse. And the other parameters are, I'm going to skip one for a second. R is L. Gravity is LT inverse, square inverse. And kinematic viscosity.
There's a ring. Yeah, no, there you go.
Kinematic viscosity is not your regular viscosity, but it has a kinematic viscosity is just L squared T inverse, so it has no mass dependence like regular viscosity. And I kind of took an intuitive guess here that they define two densities here, your density of the ball and your density of the fluid. And so just intuitively, heavy things sink and light things will float. So I kind of made a guess of, it's a buoyancy problem, so it's dependent on the ratios between these densities. So rather than defining each of the densities as their own sort of terms, I set up rho B over rho F as already a dimensionless ratio, or as a dimensionless ratio. So those were essentially the way I set up and defined my variables. So then if I scroll down over here and write that out, it becomes LT inverse is equal to L to the A, which was the radius, LT minus 2 to the B, which is our the acceleration gravity, and then your kinematic viscosity, L squared T inverse. And I'm going to ignore it for now, but the basic idea is that, that rho b over rho f is already another pi group or a dimensionless function off to the side. And so this leaves, just three variables with three equations, making, the solution pretty simple, just a solution of linear equations. So that's a plus b plus 2c equals 1, minus 2b minus c equals minus 1, and 2b plus c is equal to 1. And I solved for everything in terms of c. So that was sorry, we're still left with the situation of three equations for three variables with two equations. So, you can solve for everything in terms of c. So a is equal to 1 minus 3c over 2, and b is equal to 1 minus c over 2, since we've taken out any mass terms in this equation. And then if you plug that back in, now we have your velocity is proportional to r to the 1/2 minus 3/2 c, g to the 1/2 minus 1/2 c, and kinematic viscosity to the c, and a dimensionless term or unknown function of rho b over rho f over there. And so this is sort of our dimensionally reduced form. And you can also rewrite this a little bit by taking advantage of our by separating some of the exponentials. And so I wrote it in this form: rg square root nu over rg square root to the power of c, and then your phi term, rho b, rho f. And I didn't write all the alphas because I was delinquent, but you can kind of assume in this case that alpha is inside the phi term over here. And so looking at this, this is what I called my solution to the first part. If you were to say compare this to your Stokes formula, you can see a lot of similarity there by rearranging the Stokes formula slightly.
So sorry to interrupt. So you have three unknown variables and you have three equations. So you should know the C, right?
We do not have three equations.
Well, that's what I'm a little confused about, because you have three written down there.
I miscopied that down.
Okay.
My bad. This is not an extra equation. It was just two equations. I didn't read my own handwriting.
If I understand correctly, the third equation doesn't help us because there's no mass on either side of the equation, so we don't know. So mass is kind of 0 equals 0.
Yeah.
Would be that equation. So you have two equations and three unknowns. Is this how everyone else arrived at this as well? Yeah. I think there was a little confusion there because three were written down, but two of them were identical, just with a -1.
My mistake. Sorry.
No, it's okay.
I was misreading my own thing. I'd rewritten it back.
And just to be a little bit clear, if I wanted to be kind of pedantic and mathematically picky, phi is your unknown function of your dimensionless densities.
Mm-hmm.
At this point, you could also just say, you could take phi, add a second term in there like we did on the top of the screen there, and pi 2 would be the dimensionless quantity of your kinematic viscosity over r to the 3/2 g.
Yeah, so this would be.
So you really have kind of like root rg times some unknown function that takes in two parameters, or takes in two arguments, I should say, and spits out a number.
Yeah, and so essentially, if you did it out where you had, your instead of taking the ratio of phi b phi f from the start, or rho b rho f from the start, you would still probably end up with these two dimensionless functions or parameters. But if you compare that to what they had for Stokes' law, 2g r squared rho b minus rho f all over 9 nu rho f, I rearranged this and rewrote it as where is it? G r squared over nu times 2/9 times rho b minus rho f all over rho f, which, you know, you can group your rho f or separate rho f to rho b over rho f and rho f on over that. So this term over here can also just be seen as, you know, rho b over rho f minus 1. And if you look at the equation like this, suddenly it looks very similar to the result we had from earlier, where if c is just equal to -1, then the equation simplifies into this format where we assume your dimensionless parameter phi1 rho b over rho f is equal to 2/9 times this guy over here. And that's sort of how you reconcile this solution with what we got for Stokes' law.
Excellent. Questions? Anyone get something similar?
Well, I sort of included all the variables like the densities instead of taking a ratio. But then it sort of equaled out in the end where I got like a function with two different pi variables. So.
Yeah, that's kind of the point I was going to make, is that the assumption that was made at the beginning here of kind of taking that dimensionless ratio, if you didn't think to do that, if you did your dimensional analysis, you should probably, it should shake out as a dimensionless parameter and be in a second pi group, because you have two pi groups here.
Yeah.
And if you didn't kind of take them as, I'm going to assume that that's a grouping together, which is a reasonable thing to do kind of from your intuition. If you didn't know that, you should arrive at it the same way and arrive at it as a second pi group. So that's fine kind of either way. It should shake out. I think that's the nice kind of part of this.
I think I didn't understand the subtlety with the pi groups and the dimensionless functions when I was doing this yesterday.
No, that's okay. Yeah, hopefully now people do. All right, we are out of time. I want to just quickly say, did everyone find that the time of ice melting is proportional to area on the last problem? If you don't know anything about the Ice King of Boston, you should wiki search him. I live in Jamaica Plain, and Jamaica Pond was one of the places where they would go and excavate huge ice cubes, like massive blocks, and then pack them in hay and ship them all over the world. Seriously, it's a really cool story. And it's actually kind of wild because as he's doing this, Frederick Tudor is doing this, he's patenting all of these ways of storing ice like in hay for long periods of time. Unbeknownst to him, there are patents being filed on creating the first refrigeration systems. And so the downfall of the Ice King was rather rapid. But it's a really cool story in terms of how ice was formed and stored and shipped around. But hopefully for the mathematical part of it, hopefully you all arrived at the time should scale as length squared, which should match your intuition. This is not anything new, but you can at least use kind of math to prove that idea that like it's surface area that matters if you fix volume. So we don't have time to go through it. What's that?
One quick question: when we say it's proportional to length squared, it doesn't matter if we have an additional term to the side of like S over K or something.
Right. Yeah. Well, this was mainly to say why do smaller ones melt faster? Well, if it's a surface area to volume ratio, you should see surface area appear as the dominant term. There's other things that matter too, but the idea would be that it should be surface area, not length and not volume, that would control it. So, all right. Thanks everyone. We're a couple minutes late. On Thursday, we're going to walk through a paper and then we're going to get into non-dimensionalizing equations.